Now that we know what the number of protons will tell you about an atom, it's time to talk about what does the number of neutrons tell you about an atom. So while all atoms of an element are going to have the same number of protons, they may have a different number of neutrons. So let's take a look one more time at our example of carbon here. So the carbon that we've been looking at is carbon 12. It's got 6 protons, hence it's carbon. And it has, in this case, because the mass number is 12, it also has 6 neutrons. So if we were to do some accounting, let's do protons and neutrons. And this carbon 12 has 6 protons and 6 neutrons. But on our planet, not only do we have atoms of carbon that are carbon 12, we also have atoms of carbon that are carbon 13. In this case, still 6 protons, otherwise it wouldn't be carbon. But because the mass number is 13, that indicates there's 1 extra neutron over carbon 12. And so the number of neutrons is 7. There is also yet another form of carbon on our planet, which is carbon 14, which looks like this. Again, still 6 protons because this is an atom of carbon. But now we have still 1 more neutron in the atomic nucleus for a total of 8. Now, these 3 atoms of carbon, carbon 12, carbon 13, carbon 14, are called isotopes. So isotopes are 2 atoms of an element that differ in the number of neutrons. So you can compare carbon 12 to carbon 13. Those are isotopes. 12 to 14 isotopes, etc. Now, some isotopes are stable. Others are called radioactive isotopes. So the stable isotopes stay, the atoms stay as they are. They don't change. It's just, that's the way they are. But the radioactive isotopes of elements, they are unstable. They have so much energy that they don't know what to do with it, right? And they sort of want to reach a more stable state, so they release energy. They release this energy, which we call radioactivity. And so if we go back again to our example of carbon here, carbon 12 and carbon 13 are both stable isotopes on our planet. It's carbon 14 here that is a radioactive isotope. Now, there are lots of different kinds of radioactivity, and usually you think, when you hear the term radioactivity, you think bad, right? Bad, energy causes damage, can cause cancer. So while this is true, in some cases, there are different forms of this radioactivity. Some forms of radioactivity are really weak and they wouldn't even be able to pass through tissue paper, much less the top layer of dead skin cells in your body. They wouldn't harm you. But there are other forms of radioactivity that could go through walls, right? And definitely could go through your body, causing damage to your cells. Now, we're not going to go into the different kinds of radioactivity, and we're going to keep this example kind of simple, but just to show you. So when you have carbon 14, this is a radioactive isotope, it's unstable, and it's going to decay. When it decays, again, this is just looking at it very simplistically, what happens is one of these 8 neutrons that it has splits apart, right? And so when this 1 neutron splits apart, you lose that neutron. So we're going to go from 8 down to only having 7 neutrons. And when that 1 neutron breaks apart, it breaks apart into a proton and an electron. The electron zooms off and it's gone, and that's the energy that we call radioactive energy, and it leaves the atom. But the proton stays. It stays within the atomic nucleus. So now this atom has gained an extra proton. So we went from 6 to 7 protons. So now if we think about this, right, and we were to take these new numbers of our atom now, and our atomic number is now 7. Our mass number is going to be the addition of the 2 7s is 14. What goes here as the element symbol? It's no longer carbon, right? Because carbon has 6 protons. This guy's got 7. If we look at the periodic table of elements, you'll notice that 1 space over from carbon, the 7th element is going to be nitrogen. So in this case, it's going to be an atom of nitrogen. So when carbon 14 decays and it releases that energy, it converts from an atom of carbon to an atom of nitrogen, which is definitely very cool. Now, if we go back to our slides, there are different elements that have radioactive versions of their atoms, meaning they have extra neutrons and they have to get rid of that energy. Now, when we think of radioactivity, we think bad, but we have utilized radioactive isotopes as diagnostic tools in medicine. So, for example, you can create a radioactively labeled tracer that can locate cancerous tissue, which is highly dividing cells in these tumors. And pairing that tracer, that radioactive tracer, with an imaging system like a PET scan, you can actually see where that tumor is growing in an individual so you can better treat it. And that's kind of what you see in this image right here. You can use radioactive isotopes to assess how well kidneys are functioning. So you can give, again, a radioactive tracer to a person and see how quickly the kidneys clear that radioactivity into the urine. If it clears out really well, great. If it doesn't, the kidneys are not doing their job very well. And then one more example. So we talked about iodine earlier in this chapter and how it's one of those trace elements that we need for proper functioning of the thyroid. If your doctor suspects that you have a thyroid issue, they might, to help diagnose, they might give you a radioactive version of iodine, which then would collect in your thyroid, and they can see how well that would be processed, giving the doctors an indication of your thyroid health. I had a friend when I was in graduate school. She worked in the same lab as I did, and her doctor suspected she had a thyroid issue. She went to the doctor. They gave her the radioactive iodine. She came back to the lab, and being the nerds that we are, we took our little Geiger counter, which is an instrument that helps to detect radioactivity, and it crackles when it's in close contact, and it crackles more when there's more radioactivity. And so he took the Geiger counter, put it up to her throat where her thyroid is, and the thing went just crazy crackling. It was a little unnerving, but also definitely very cool. And so, when we use radioactive isotopes as a diagnostic tool, we kind of have to, play a little bit of checks and balances here. Is it appropriate to expose somebody to a small amount of radioactivity, but be able to diagnose a more harmful disease or disorder, or maybe it's not worth the risk? All right, so protons will tell you not only the atomic number of an atom, but also will tell you which element you have. Number of neutrons will tell you which isotope of that particular element you have. Lastly, we move on to electrons. And these are a little bit more tricky and also a little more interesting, perhaps. So before we talk about electrons, we have to talk a little bit about energy. This is because electrons have a certain amount of energy associated with them, and this is important for understanding how they contribute to atoms of elements. So first of all, taking a couple steps back, energy is the capacity to cause change. There are different kinds of energy. We're going to focus on two main types in this course. So we're going to talk about potential energy, and later on we're also going to introduce kinetic energy. That's a nice little preview. If you can't remember, kinetic energy is the energy that's associated with motion. So things that are moving have kinetic energy. The other kind of energy is potential energy. This is what we introduce here with the electrons, because electrons have a certain amount of potential energy. So potential energy is the energy that matter has based on its location or its structure, right? So a really complex molecule that has a very complex chemical structure will have a lot of potential energy. Or a ball on the top of a staircase, because it's located up high, it's going to have a lot of this potential energy. And so going back to electrons in an atom are going to differ in the amounts of potential energy that they hold. And so an electron's state of this potential energy, this is called its energy level or electron shell. And depending on how much energy an electron has, it'll be either closer or farther away from the atomic nucleus. So if we take a look at the diagram down at the bottom, this is showing you sort of a quarter of a full atom. So you've got your atomic nucleus, and then you've got these concentric rings that are drawn around the atomic nucleus. These are sort of the orbits that the electrons can take around that atomic nucleus. And you'll notice these energy levels or these shells get bigger and bigger as they move further out from the atomic nucleus. And the way the energy is associated here with this drawing is that the electrons in the first shell, or the one that's closest to the atomic nucleus, these electrons are going to have the lowest amount of energy. And then as you move with each subsequent shell further away from the atomic nucleus, the electrons have more and more of this potential energy. And what's cool is that electrons, they don't have to stay in that shell that they're originally in. They can actually hop between shells. They don't spend a lot of time in between the shell, but they can move between them. This is kind of like a ball on a staircase, which you see a diagram of in the upper right-hand corner there, right? A ball can sit on any one of those steps. It can spend time there, but it really doesn't spend a lot of time in between the steps kind of hanging out in midair, right? Thanks to gravity. So the same thing for the electrons, right? They can sit in each one of those shells and they can move between them. They just don't spend a lot of time in between. Now, if an electron wants to move shells, it's going to have to either give up or accept extra energy so that it has the right amount of energy to sit in that other energy shell. So let's think about this for a second. I'm just going to use arbitrary units for this example. Let's say the electrons in the lowest energy level have 1 unit of energy, second shell, 2 units, third shell, 3 units of energy. Let's say an electron in that first, smallest shell wants to move to the second shell. It's already got 1 unit of energy, but to be able to exist in that second shell, you need 2 units of energy. And so this electron would have to absorb 1 extra unit of energy from its surroundings to have enough to sit or to exist in that second shell. The same thing goes if, let's say, an electron in the third shell, the one furthest away in this diagram, with 3 units of energy, it wants to move all the way down to the first energy shell. It's got 3 units, but if you want to hang out in that first energy shell, you can only have 1 unit. So that electron will have to give up energy to its surroundings to lose those 2 units so that it only has the remaining 1 and can happily exist in that first shell. And this concept is going to come back to haunt us when we talk about photosynthesis, because the absorbance of light by pigments has everything to do with electrons jumping these energy shells or energy levels. So hold on to this thought after we finish with chapter 2. Okay, and so why is this important? Understanding that electrons have energy and they sit in these shells, which is a representation of the amount of energy they have. Well, really the chemical behavior of an atom is going to be determined by how the electrons are distributed in those electron shells. And so what we're going to do is we're going to go back to the periodic table of elements and we're going to look at how the electrons are distributed between the different elements. All right, so this particular periodic table of elements looks a little bit different from the one I showed you earlier. The one I showed you earlier was the full one. And so what you see on the previous slide is really just the first 3 rows of the periodic table. So if you look on this table at the first 3 rows, you'll notice that there's a big gap in the middle of the first 3 rows. So all we've done on the slides is we've removed that gap and we made sure that beryllium is sitting right next to boron, magnesium is sitting right next to aluminum. All right, so there's your boron and beryllium and aluminum and magnesium there. Okay, now this particular periodic table shows you electron distribution diagrams. Those are those funny concentric circle looking things. So first of all, we have to determine, well, how can we tell how many electrons does each atom have? We haven't talked about this yet. When you're looking at atoms of elements on the periodic table of elements, they are all what we call in their elemental form, which means that all of these atoms are neutral in their charge, right? So they're not positively charged, they're not negatively charged. So if hydrogen, the first element, has 1 proton that has 1 positive charge, in order to be neutral, this guy's going to have 1 negatively charged electron to balance out with the positive proton to be a neutral atom. Same thing for helium. 2 protons, second element, has to have 2 electrons.